Some general solutions of differential equations, especially homogeneous differential equations, use linear combination. And to learn more about linear combination, linear dependency, or independency should be understood. Let's discuss them here in Engineering Math 5. Say there are two differential functions of x, f of x and g of x. When they are combined with some respective constant c, they should equate to 0. Mathematically, we can stress the idea this way. c1 times f of x plus c2 times g of x is equal to 0. So again, if they equate to 0, the functions are considered linearly dependent. And if the situation is otherwise, the functions are said to be linearly independent. So how do we check linear dependency of functions? In case of just two functions, using the same principle that their summation with some constants should be equal to 0, we can then say that these two functions should be equal. And if we simplify the first term, like making c1 as 1, then we can say that f of x should be equal to a constant c times g of x, to say that they are linearly dependent. Let's understand the concept further with some examples. Check the two functions for dependency. y1 is equal to t and y2 is equal to t squared. As we said that the first function should be equal to the second times a constant, we get t is equal to c times the square of t. At this point, there is no way for us to plug a value of c to make the equations equal, so these functions are linearly independent. Next example. Check dependency or independency of y1 is equal to x squared minus 25 and y2 which is equal to x plus 5. Equate them together with c, so we have x squared minus 25 is equal to c times the quantity of x plus 5. The left side of the equation can be expanded to the quantity of x plus 5 times the quantity of x less 5, where we can notice that the quantity of x plus 5 can be cancelled out, showing that c is equal to x minus 5. And what we got is a function instead of a constant, so the functions are again linearly independent. How about the two functions for checking this time? y1 is equal to 5 times sine squared of phi, and y2 is equal to 1 less cosine squared of phi. Equating them both, we get 5 times sine squared of phi is equal to c times the quantity of 1 less cosine squared of phi. Now let's recall our identities stating that sine squared of an angle plus cosine squared of an angle is equal to 1. So we can arrange terms to have sine squared phi is equal to 1 less cosine squared phi. And these two are what we have in our functions, so we can actually cancel them out, leaving us with c equal to 5. 5 is a constant, so we can say that the functions are linearly dependent. Let's have this example with the functions y1 is equal to 6x minus 9 and y2 is equal to 10x minus 15. Equate them again. If you analyze deeper, you would notice that there is similarity of the two binomials. 6 turning 9 by multiplying it by 1.5 and 10 turns to 15 by the same 1.5 multiplier. So the functions might be dependent. In order to identify the constant c, it is easier if we check the functions separately by terms. Starting off with those with x, we have 6x upon 10x as c, so cancel x and simplify the fraction to have 3/5. Do the same with the constants and get negative 9 all over negative 15, where c is also taken as 3/5. Thus, we can show the combination as 6x minus 9 is equal to 3/5 of the quantity 10x minus 15. and conclude that they are linearly dependent. How about more functions to be checked for dependency? If there are more functions than 2, revert back to the definition stating that C1 times f of x plus C2 times g of x plus C3 of h of x and so on are combined, and these should be equal to 0. Let's have some examples. We have y1 is equal to 4x squared minus 3x, y2 is equal to 5x, and y3 is equal to x squared to be checked for dependency. From the standard form, plug the three functions, then analyze how to get everything equal to 0. In this case, check the terms with x squared and those with x. So if we let C1 be equal to 1, we can have 1 times 4x squared and C3 times x squared, and they should cancel out, so we can see that C3 should be negative 4. Similarly, 1 times 3x should cancel out with C2 times 5x, which shows that C2 will be equal to 3/5. So we identified all constants to make the equation be equal to 0. Let's check. Placing all constants into the equation will make it turn into 4x squared minus 3x plus 3x minus 4x squared is equal to 0, where we can cancel each term, giving us 0 is equal to 0. So the functions are linearly dependent. How about for longer functions, such as what we have in this next example? Again, plug the functions into the equation to incorporate the constants C1, C2, and C3. Then expand the binomials. Regroup the terms according to variables, so take all with x in one group and the other with constants remain in one group. Then next is to extract out x from the first quantity and note that these are equated to 0, which is also translated as 0x plus 0. So by using ZPP or zero product principle, we can equate both groups to 0 where x cancels out on the first equation. Then what we have is a system of linear equations. And by the method of elimination, multiply the second equation by 2 to eliminate C3, and the resulting equation is 11C1 plus 9C2 is equal to 0. We can arrange this to have C1 as a function of C2. So if we assume C2 as 11, we can then compute for C1 as negative 9. If we plug the two constants back in either equation, say the first equation, we can identify the value of C3 as 7. So we are able to identify constants to make the combination of the functions equate to 0. Let's check the constants on the second equation. We were able to come up with 0 is equal to 0. So now we can conclude that the functions are linearly dependent.